Welcome. Today we are going to discuss how integration is nothing but antiderivative, what we have learned from our school days. So, towards that, this is the first fundamental theorem of calculus. This is the first fundamental theorem. We name this FTC, fundamental theorem of calculus 1. Okay, what does it say? It says that let f from a b to c be a continuous map function define f of x, this is equal to a to x f of t dt, because f is a continuous function. So, this is Riemann integrable, therefore, a is less or equal to x is less or equal to b, x is a point between a and b, then f is differentiable and f prime of x is nothing but equal to f of x. That means, this capital F is nothing but the antiderivative of f. Okay, so, as you can see in this theorem, we are assuming f to be continuous. So, now in order to see that, so let us look at, if I want to show that f is differentiable, then f of x plus h minus of f of x, if we want to write, then this is going to be a to x plus h f t dt minus a to x f t dt, and which by the property of integration what we have studied earlier, this is going to be x to x plus h f t dt. Now, f is a continuous function. So, in the last lecture what we have done is that the average x plus h minus of f of x divided by h, this is equal to 1 by h x to x plus h f of t dt. This is going to be by the mean value theorem for integration, this is going to be equal to f of c h. For some c h, this c h belongs to x to x plus h. This is what let me write it more carefully. This is, as we are interested in taking h goes to 0. So, as f is a continuous function, given that f continuous, therefore, for every epsilon positive there exists a delta greater than 0 such that mod of h less than delta will imply mod of f of y minus f of x is less than epsilon for y belongs to x minus delta to x plus delta, or rather this is also for our purpose what we can write it to be for all y belongs to x plus h. Okay, we can find small h such that for all y belongs to x plus h, mod of f y minus of f of x is less than epsilon. So, our C h is lying between this x plus h. Therefore, so mod of f C h, what we have taken f of x, this is less than epsilon. Therefore, by the definition of the derivative, f is differentiable. F is differentiable and f prime of x is equal to f of x, as here you can see that f of C h, this goes to f of x as h goes to 0. Rather, limit h goes to 0, f of C h is equal to f of x. So, what you are going to get is that f prime of x is equal to f x, capital F prime of x is equal to f x. Well, here we have assumed continuity of small f. Now, suppose one can ask that we are dealing with Riemann integration. Why do we need to impose one extra condition that f is continuous? Certainly, if f is continuous, f is Riemann integrable, but we have seen that there are discontinuous functions which are also Riemann integrable. So, let us see that if we assume assume f from a b to R Riemann integrable. So, definitely a to x for x in a b, a to x f t dt, this is well defined because this is Riemann integrable, call this as f of x. Now, what can we say about this capital F? Fundamental theorem of calculus, we have proved that if small f is continuous, then this capital F is differentiable. Now, here we are assuming only the small f is Riemann integrable. Now, let us see f of x plus h minus of f of x. This is equal to, as we have noticed, x to x plus h f of t dt. Now, if I take the modulus, then this by the previous properties of Riemann integration what we have done, I can put the mod inside and take, because f is Riemann integrable means we are talking f is a bounded function. So, therefore, this is less or equal to some m times this b minus a, here b minus of a is h. Now, this goes to 0 as h goes to 0, because this is also greater or equal to 0. Therefore, what it says that if we are assuming only Riemann integrable, then the capital F is definitely going to be a continuous function. So, f is continuous, capital F is continuous. However, we do not know whether we are going to get a capital F to be differentiable. So, towards that, let us consider example, let us consider f of x, this is equal to half when x is less or equal to half, and this is equal to 1 when half is less than x is less or equal to 1. So, certainly this is a discontinuous function, it is discontinuous at half, and it is Riemann integrable, that what we had seen earlier. So, therefore, what it is going to be now capital F of x, if we want to continue, this is 0 to x f t dt. Now, if our x belongs to 0 to 1/2, then capital F of x is equal to 0 to x half dt, which is equal to 1 by 2 of x, x by 2. Now, if x belongs to half to 1, then f of x, this is equal to 0 to half f t dt plus half to x f t dt, which is equal to x by 2. This is equal to half then x, this is 0 to half, minus half to x is 1. So, this is x half to x. So, this is t. So, this is equal to 1 by 4 minus x by this is minus of x, oh I am sorry, here it is plus x minus half, which is equal to x minus 1 by 4. Now, you can see that f, this capital F is a continuous function. However, if I want to get for h positive, f of x plus h minus of, let us say, f of half plus h minus of f of half divided by h, this is equal to half plus h minus 1 by 4, because this is what we are taking h to be positive, minus of f of half. Let me write it in the separate page. Now, for h positive, f of half plus h minus of f of half divided by h, this is equal to x. If x is greater than half, capital F of x is x minus 1 by 4. So, this is minus of 1 by 4 minus of f of half is going to be 1 by 4 divided by h. So, this is 1. Now, if h negative, f of half plus h minus of f of 1/2 by h, this is half plus h, h is negative. So, it is on its less than half, therefore, this is going to be x by 2, which is 1 by 2, 1 by 2 plus h, and minus 1 by 4 divided by h. So, this is going to be h by 2 h, and this goes to 1/2. So, as you can see that f is not differentiable at half. So, fundamental theorem of calculus, in order to get the differentiability small f, the function which we are integrating, if that function is a continuous function, then definitely there is an antiderivative, that is what is called the f prime. Okay. Otherwise, what we can get is that only this integral is continuous, but it may not be differentiable. So, in order to get the antiderivative, we need to put little extra condition on our function f. Okay, so using this, let us get some example of this. One of a nice example as an application of the fundamental theorem of calculus is that let f be a continuous function on R, okay, and it satisfies f of x plus 1 is equal to f of x for all x belongs to R. What does it say? This is actually one periodic. So, this is 0 1, this is 2, this is this is 3. So, now in the 0 1, suppose our f is looking like this, then on 1 2 the f will also look like this, exactly the same copy. Even on minus 1 0, this is the same copy. So, this is you take the copy of 0 1 and then you put it everywhere in the 1 2 2 3 4 5 any n plus 1, they will look exactly the similar. That is what we call this type of function as one periodic function. Then integral 0 to a to a plus 1 f t dt is equal to integral 0 to 1 f t dt. So, now what in the integral we have said that this is the area under the curve. So, now if I take any, suppose this is what the area under 0 1, now I take any a here and then a plus 1 is here. So, now the area of this is also going to be the same as integral 0 to 1 f t dt. That is what is about true about continuous one periodic function. So, now you can see that you define, if I have a to a plus 1 f t dt. Now, this is a function of a. So, this function let us call me as g of a. Now, this g of a as a function of a and this f is continuous. So, what we have shown is that this is going to be a differentiable function. So, we can compute the derivative. So, now if we can show that the derivative of this g prime of a, this is g is prime of a is constant, then we derivative of g is 0, then we can say that g is constant, right. So, now once it is constant, this will be true for any choice of a, and in particular we will take a to be equal to 0. So, now let us calculate g prime of a. So, g prime of a, this is equal to d by dA, let us write in this term. This is 0 to a plus 1 f t dt minus 0 to a f t dt by the properties of. Now, as you can see that this is nothing but so this is d by dA of f of a plus 1 and minus this is capital of f a. So, which is equal to derivative, this is the antiderivative because capital F is the antiderivative of f. So, this is f of a plus 1 minus of f of a. It is given to us that f is one periodic. So, this is equal to 0. Therefore, g is constant, that is g of a is equal to g of 0 for all a belongs to R, that is integral a to a plus 1 f t dt, this is equal to integral 0 to 1 f t dt. So, So, this is a nice application that if you have copies, then it does not matter where, you just need to consider to find the area, to consider the interval of the length 1, then that is going to give you the same area as you are going to get from 0 to 1. Now, another example which is also useful, let f from 0 pi by 2 to r be continuous. Given that f is such a continuous function, given that 0 to pi by 2 f t dt is equal to 0, then so that there is a such that f of c is equal to 2 cos 2 c. So, f of x equal to 2 cos 2 x has a solution in this. You take any continuous function whose on 0 to pi by 2 and whose area is 0, then what we can actually find that there is a solution. This curve f of x is going to cross 2 cos 2 x at some point, that is what it is saying. Okay. So, now you define g of x, this is equal to 0 to x f t dt minus sin 2 x. Now, g this first is a differentiable function because f is continuous. Fundamental theorem of calculus says that this is differentiable and derivative is nothing but f, and this is also a differentiable function. So, I take g prime of x. Now, this is equal to f of x minus this is 2 cos 2 x, this is what the g prime. Now, as you can see that g of 0, this is equal to 0 to 0, this is 0, sin 0 is 0, 0. G of pi by 2, this is equal to 0 to pi by 2 f t dt, which is given to us to be 0. So, this is 0 minus sin 2 pi by 2 is sin pi, which is also 0, 0. Now, g is a differentiable function and g of 0 is equal to 0 and g of pi by 2 is also equal to 0. Then our old friend Rolle's theorem tells that there will be some c such that g prime c is going to be 0. So, by Rolle's theorem, g prime of c, this is equal to 0, that is f of c, this is equal to 2 cos 2 c. Okay. So, this is an interesting application of fundamental theorem. You see, any continuous function whose area under this curve is 0, then what you are going to get is that it is going to cross 2 cos 2 x. Okay. So, now the question is that what we know that if integration is nothing but if I take a function, fundamental theorem of calculus says that integral 0 to x f t dt, f prime is capital F prime is f. How to now the question is that how to evaluate this integral. So, what we do is that if we what we have studied that if we have the integral of f of x is equal to the antiderivative plus c, that is what we have learned in our school. So, now let us get that. So, fundamental theorem of calculus 2. So, let f from a b to r be continuous and capital F is a B, any antiderivative of F. That is, we have studied, that means capital F prime is equal to f of x. It can be any antiderivative. What we have seen is that if f is an antiderivative, then f x plus c is also an antiderivative. Okay, then integral a to b f t dt is equal to capital F b minus of f a. So, this is precisely what we had been told in our school days. So, now the proof, let g x is equal to a to x f t dt. Then definitely what we know, that g prime of x is equal to f of x by fundamental theorem of calculus 1. Now, g is also an antiderivative of f, small f, and capital F is given to be antiderivative of f. This is another antiderivative. So, two antiderivatives are nothing but the difference of them is constant. So, g of x, this is plus c, this is equal to capital X for some constant Okay. So, f of b minus of f of a, this is nothing but g of b plus c minus g of a minus of c, which is equal to g of b minus of g of a. Now, what is g of b? Now, g of b is nothing but a to b f t dt, and g of a is a to a f t dt. Now, a to a f t dt is equal to 0. So, this is equal to a to b f t dt. So, before getting into some examples, so let me remark certain thing. So, what does this says? This says that if f prime is continuous, then integral of a to b f prime of t dt, this is equal to f of b minus of f of a. This is what this theorem is saying. You see, is it required? So, what one can show is that if we impose just the condition that f prime is Riemann integrable, then this left hand side makes sense. F is a differentiable function and f prime is Riemann integrable. Now, this is equal to f b minus f a. So, this in fact is true. So, you are going to read it in some advanced calculus course. I am not going to prove this. However, if we assume, what we have seen is that if f prime is continuous, then what we have assumed is that this is true, this with little additional hypothesis. So, this raises a natural question that suppose f is a differentiable function, that means f prime exists. Is it necessarily be true that f prime may not be, we have seen that f prime may not be continuous. So, will it necessarily be true that f prime may not be integrable even? So, I mean, do we need to impose the condition that f prime is Riemann integrable or f prime is continuous? Will it not happen automatically. That is what we are going to see it in the next lecture. Thank you.